thank you for the invitation first. It's a very nice place. It's a long title because it's a sort of review of some papers jointly with Mario Garcia Fernandez and Carlos Garcia Prada. See the first three. They are from ICMAT too, and Vansi Pingali joined in the fourth one, and Chen Zhao more recently joined. So it's very good that Martin gave the talk before, because the kind of problems I want to talk about is kind of gauge maps, or equations for gauge maps coupled to Kähler metrics. So there is a new variable, which is, now the metric is not fixed. Okay, it's part of the problem. The philosophy I will take to guess which questions I should look for is as far as I know, due to a T and box. And many of you may not, but maybe some people are not familiar. So the point is that I don't know, very vaguely, two gauge equations are often arising as zero mapping conditions, no? Vanishing on moment maps on infinite-dimensional symmetric syntactic manifolds, and very well-known cases, the action of the gauge group G on the space of connections. Say on a compact Kähler manifold. In this case, you obtain the Hermitian Yang Mills equation as a moment map condition, a vanishing of a moment map. Okay. And that's a link that in the morning Daniel referred to a little bit. Maybe written in a different way. Something like this. The curvature 2 form contracted with the metric is a multiple of the identity. Mm-hmm. So I want to find moment map conditions in some other settings that give you nice PDEs. Okay, and this is useful to construct moduli spaces as scalar reductions. Okay. So first, I won't couple the gauge map only the gauge field, and this is the first part. The first work we did is actually this way in Mario's thesis, supervised by Oscar and myself, and later published in Geometry and Topology with some more stuff. So in this case, since there is no gauge map, we just start with a compact complex manifold that emits some Kähler structures and the holomorphic vector bundle. And then there is a group activity where I will explain later, on a symplectic manifold, for which these are the conditions for the vanishing. Okay? So the unknowns are a Kähler 2 form. It must be a 2 form compatible with a symplectic 2 form compatible with a complex structure, and a Hermitian metric on the bundle. Okay, and these are the two equations. Actually, I'm simplifying. You can do it for principal bundle, but let's focus now vector bundles for this introduction. Okay, so FH is, as I wrote there, the curvature 2 form of the chain connection of the Hermitian metric. Lambda means a contraction with the metric. So since this trace it's a 4 form, when you contract twice you get a function. So this equation is well defined. S is the scalar curvature of the Kähler metric. Okay, and you have to fix some alpha, some constant, to couple the metric and the connection. Okay. In this case, the chain connection. So now well, as I said, there is a simplex interpretation I will explain later. But now I want to use some kind of gauge maps. I mean, I will start with some linear representations that come from quiver theory, just because they arise from these equations. So we start with this example. We have, as before, a compact quiver complex manifold and a quiver, like this one. Okay, so with some vertices, arrows, and now I define a holomorphic quiver bundle as a representation of the quiver in the category of holomorphic vector bundles. Okay, so it's a family of bundles attached to the vertices, and the morphisms is attached to the arrows. Okay, this is just a representation of the quiver. And here you have the diagram for a quiver bundle. As before, we fix some Hermitian metrics, okay, on the bundles attached to the vertices. And I will define some equations. I will see how they come from the other equations, okay? So the equations maybe they look too long, maybe, but actually the vortex equation that Martin was writing is one example. For this quiver, okay? Then phi is just a section of E. Okay. So maybe you can see. Okay, this is the usual. I mean, it's a quiver theoretic version of the usual self-dual vortex equation, and this one, okay, involves this scalar curvature. These terms that will be later, I mean, they vanish on Riemann surfaces, and that's the case we will study, okay, because this is a 4 form. And so the only surviving new term is this. So it's a Laplacian with respect to the geometry. Shifted to this. So I will explain how these come, how these appear. So the method they do is by dimensional reduction from the Hermitian Yang Mills, from the Kähler Yang Mills equations. So I'll start with Kähler Yang Mills. So now, fix something that is like manifold. Okay, so P is a parabolic subgroup. Then there is this, it's not difficult to prove that if H acts trivially on the first factor here, then the equivalent vector bundles are the same thing as quiver bundles on X for some quiver with relations actually that depend only on P. I mean, the vertices are just the reducible representations. It is just like of P. It's just like an anisotropic decomposition, and then you need, because for P there may be representations that are not reducible, then there is some extra data that is encoded in the errors. Okay. So, just to give an example, you can compute. This is the quiver you get when the flag manifold is a complex projective space plane, and well, the relations are just general mass commute. So it's a computation to see that if you write the Kähler Yang Mills equations that I wrote before, so they were written like this. If you write them on this complex manifold, okay, by the equivalence I wrote before, if you look at solutions of these equations that are invariant under the action of the maximal comparator group of H, they're actually equivalent to the Vortices equation. This is a long computation you can do, and that's what you get. It's not the first time people have done this. This was done earlier by Witten. I think 70s later, and later without for some groups. And later, yeah, I mean, there is a long history. Garcia Prada did something else. And yeah, actually, he obtained it this way some of the theorems that Martin mentioned. Okay, so this is the theorem I just mentioned. So you can find some constant for which Kähler Yang Mills is the same as Vortices. Expressions. Only for the valid solution. Okay? Those are the ones I can describe on X. Okay, so this is maybe a little bit abstract, but as I said, if you take the complex projective line and then you can build a using phi a bundle on X and obtain the equation Martin wrote, and this other one. Okay. So the metric is now an unknown. And we call these the gravitating Vortices equations or self-dual Einstein-Maxwell-Higgs equations. And maybe I can say C is a constant. C is determined by alpha and the topology. You can just integrate and see it's fixed. Okay, so we call them gravitating because maybe this metric can be thought a little bit like gravity. But I should say that in general, these equations have no physical meaning. As far as we know, we asked to many physicists, but later we will see that there is a case in which these do. Okay? Actually, that's what I'm going to say. So, we found, it was a surprise for us, that physicists have studied those equations when C is 0. Okay? They call them the Einstein-Bogomolny equations, and they arise in a different way, also by dimensional reduction, if you like. But you start with a Lagrangian for the abelian Einstein-Higgs equation theory for some order parameter, given the Bogomolny phase, and on this four manifold, and there are invariant in these variables. Okay, so this is. I mean, I learned this from papers by Yifang Yang, but there is a lot of literature, and they seem to be a model for topological defects in the early universe. I mean, they are called cosmic strings. They have nothing to do with superstring theory. Okay? They look like strings. That's how they call them. And alpha, actually, it's very nice that it has the same sign. I mean, it's positive. That's what we need to have Kähler geometry. It's just a multiple of the universal gravitation constant in the theory. So we were very happy for this. But now, this was kind of an introduction of why we want to study these problems. But now I can formulate a moduli problem that may be more suitable for this conference. You start with a compact symplectic manifold, a compact Lie group, a principal bundle, and when you want the gauge map, you also add this Hamiltonian Kähler manifold that in the case of quiver, the quiver vortex equations was some linear representation. And in general, you can put anything here. And yes, in the bundle. And then you can try to construct meaning in my case as a Kähler quotient. The model is phase parameterizing. You see I'm fixing now, if you like, the metric data, and there in this other, the holomorphic data. It's a dual picture you're always doing in this philosophy. When we want to look at the moment map. So you want to parameterize complex structures that define Kähler structures on the manifold, connections that define holomorphic structures on the complexification of the principal bundle, and sections that are homomorphic for J and A. Okay, so this is the moduli we want to construct, and we could have tried with algebraic geometry. There is also a little bit done in some cases in this problem. Without actually gauge maps in boundary abundance thesis, and not the case, I think, by Hassett. Some specific cases, but I mean, there is only on curves in fact. We'll apply symplectic geometry, so the moment map, and I could anyway try to guess what the algebraic geometry problem would be, and then I would expect we are trying to parameterize polarized projective varieties together out with principal bundles and algebraic sections with some associated bundle, and by the usual philosophy I mentioned in the morning, I expect there must be a closed link between the two moduli if they exist. Okay. By theorem of connectedness, Donaldson, Uhlenbeck, and Yau, and in fact in this case, because there is a gauge map, maybe I should mention more theorem of Mondani-Riera, solving these I mean the vortex equation for gauge maps, nonlinear ones, and more recently by the theorem of Chen, Donaldson, and Sun, which solves the Kähler equation by some cases with the condition. But very little is done on these links. That's part of what we are doing. We are heading there. So I have given the setup. Okay. I will now write the equations more general than what I did before in this more general situation. But now I have to add two coupling constants, an element of the center of the Lie algebra, and then I also need an invariant inner product of the Lie algebra. Okay, that's the new data I need to write equations. So these are the equations. for a complex structure on the symplectic manifold. So that means the manifold should become Kähler with omega and j. And the connection, defining a holomorphic structure on the complexification of the principal bundle, and a section which is holomorphic. That could be written as an extra equation there. So the first equation is again up to this. I mean, you can normalize in general, but because there is this new term, I can't in principle. Well, it is useful to write them this way. This is the usual vortex equation studied in Nazi, in the generality I'm saying, but in other generality of the people. And this is, as you say, it's similar to the equation I wrote for the gauge, for the quiver vortices. Okay, so you have the two forms, the moment map, the curvature and the contraction. Now, I mean, this notation means I'm using here the inner product, okay? So in the previous cases, it is minus the trace, so that's squared. In the case of vector bundles, okay? If the inner product is minus the trace.
So, Luis, can you say maybe something more about the C that you said depends on the topology, and sometimes you want to be zero to make this connection to the...
No, that's a good question.
So how does that really work? Is there some freedom?
No, C is fixed.
It's fixed, yeah.
It's fixed by the rest of the data and some characteristic classes. I mean, I didn't write the formulas because it's knowledge. It's known. It's an interesting question. What happens when C is 0? Because that's a very special case. There may be something interesting in the nonlinear case we haven't thought about. So that's because, I mean, when C is 0, yeah, you can solve one equation and plug the solution in the other one, and that helps a lot to solve the equation. So maybe something like that happens. Okay, so maybe it's time to, well, actually you were asking this first remark. And as you see, I'm deforming these famous equations from the curvature for Kähler metrics, studied by Jonathan Tianjiao and many other people. There's a huge literature on this. So the expectation is we can bring tools from both fields, and actually they interact with each other. So that's what we are going to do. So it's now time to explain why this is a moment mapped condition. Okay? Okay. So just to remember, we have a symplectic form, principal bundle, and Hamiltonian Kähler G manifold. Then to write this moment map condition, what I need is some inner manifold. Well, actually, because I want it to be Kähler, it would be just symplectic. I will call T, it will come later. I want the action of a group. I will call G for gauge, but actually it will be an extension. And I also want some symplectic structure on this T. That will depend on the parameters alpha and beta I wrote. So I'm going to define the three objects and just say what's going on. So T is constructed using these three spaces, infinite dimensional spaces, as in ICMAT Madrid philosophy. So complex structures, connections, and global sections of these associated bundle. And it doesn't take too long to write the symplectic forms. Okay. So here, remember, this involves some invariant bilinear form on the Lie algebra. Okay, it's implicit here. This is a function. Okay, so now, well, I haven't defined yet what T is, but it will actually be inside the product of these three spaces, J, A, and S. Fine. Now, I want to define a group. And Fujiki and independently Donaldson found a moment, Hamiltonian action on the space of complex structures by the group of Hamiltonian symplectomorphisms. Okay? And one can see that the vanishing of that moment map for that Hamiltonian action is this condition. Okay, the scalar curvature must be constant. So the problem is the Hamiltonian symplectomorphisms act on X, but actually I have a principal bundle and I want to act here. I know the gauge group acts there. I could try with the product, but actually what I do is I lift it. I lift the action. I mean, this is natural to do. You define the extended gauge group as the space of automorphisms of the principal bundle. They are geoequivalent, so they cover the femorphisms. But I require that they are actually in H. Okay? So there is a map from here to there that to each automorphism G associates the Hamiltonian symplectomorphism that I will call G check. Is this map? And the kernel is the usual gauge group. So we have this group extension. What comes next? The action. Yeah, now we have to define the action. I define the action of this on the three factors, and then take the diagonal action. So for GK and Donaldson, we will study the action of G check, so I just compose. Okay. So this is just pullback. Now it may be something slightly new. We consider the action of this extended gauge group on connections that we view as splittings of the Atiyah's short stack sequence. So if you have a connection, you just compose and get a new connection. Okay, so this is the action on connections. And this is even easier. No? You can act on any associated bundle. On S. So S is a space of section of the bundle. So now we have the three actions. I define, now I said T was inside this product. So I just require some integrability conditions. I want the method to be Kähler to induce, the connection to induce a complex structure, a holomorphic structure on the complexification of the principal bundle. And I want phi to be holomorphic. And of course, I mean, up to some factors. This is the symplectic structure you would try to write. And then the calculation we make is that solutions, I mean, there is a moment map we can obtain, and its solutions, I mean, its zeros are actually the solutions of what I defined as the Kähler Yang Mills situations. And if I take positive coupling constants, then this is actually Kähler. I'm avoiding some singularity problems that may appear. This is infinite dimensional manifold, so it's very, very much formal. So the moduli space can be constructed as a Kähler reduction. So now, when you are in this situation, you have a group action on a Kähler manifold, which is Hamiltonian. There is a lot of machinery, at least formally, to try to solve this condition, the vanishing, or to find abstractions. So I will start with abstractions. So I will return to the point of view I took at the beginning. So I fix the complex structure on the manifold. The Kähler class, okay, omega, and the connection. So using the connection and the complex structure, you can construct a complex structure on the complexification of the principal bundle. I call this complex structure I, capital I. So actually, I could have better started with J, omega, and capital I. And the holomorphic section. And then in this dual point of view, it's always the way you try to solve and find abstractions in this generality. What you vary is a metric. In this case, the pair of metrics. If you think of the symplectic form as a Kähler 2 form, so it's kind of a Kähler metric. And then H is a Hermitian metric, but on the principal bundle. So that means a reduction to a compact maximal compressive group that I call EH. Okay, so EH is a reduction. And then the equations can be written this way. Okay. In terms of omega and H. So this is the curvature of the chain connection of H. And this is the scalar curvature of the Kähler metric as it's to omega. And yeah. So these are the equations. And this part of the theory was already done without the gates map. You don't need that. To study this space of pairs of metrics, or space of pairs of metrics. So it comes with a canonical affine connection, which is torsion-free and its curvature is covariantly constant. This generalization of a result by Donaldson in the case of Kähler metrics, in which actually this symmetric space is Riemannian. It doesn't happen in this generality, but we are able to find this. And an important key, an important isomorphism we use to construct this is an isomorphism that, from the Lie algebra of the extended gauge group to the tangent to the space of pairs of metrics at a pair of metric P. That is the infinitesimal action, but in the imaginary direction. Remember, I is the complex structure on the total space of the principal bundle. Okay. So this infinitesimal action in the imaginary direction will appear everywhere when you try to find stability conditions from differential geometry. Actually, now for each pair of metrics, B is, I can write it here, B is J omega, omega and H. So the symplectic structure and the Hermitian metric. For each key, there is a moment map. I just mentioned that. And I can use it to define a one form, which is essentially the moment mapping, but in the imaginary direction. This. And I can use this. This is formal. This is very, has been done since many decades. Then I can use it to define the character. Like here first in the case of Kähler, in the problem of Kähler metrics. That's why we call it Futaki invariant, because it was invented by Futaki, and it has this. This is just what you need to get a character from this Lie algebra of infinitesimal homomorphisms that fix phi. And then again, we can prove that an abstraction to the existence of solutions is that this Futaki invariant must vanish. Okay. Well, it must vanish, actually, because being a zero is the Kähler Yang Mills equation. Maybe what's not so trivial is that it is independent of the pair of metrics. So you don't need to start with a solution to compute it. So if you find a pair for which this doesn't vanish, then you know there are no solutions. I mean, there is a lot of stuff we can bring from the theory of Kähler metrics, canonical metrics or Kähler metrics. For instance, we can define, there are many kinds of stability conditions you can define. One is geodesic stability. Since this space of pairs has a torsion-free affine connection, you can talk about geodesics, and then you can define some stability condition in terms of geodesics. Okay. Yeah, there are many technical problems anyway. I mean, one doesn't expect these geodesics are smooth because it doesn't happen in the case where you just work with the Kähler metric problem. But it's known that there are, I mean, this space B, when there is no H, is a space of Kähler potentials. Okay? And in this case, it's known that it's convex by weak geodesics, by C11 geodesics. I mean, any two Kähler potentials can be joined by geodesic. So one has to enhance this, but there are many technical issues we haven't. This is a work in progress. Okay. And the last abstraction, I mean, this is all, if we are able to work with weak geodesics, then this is another abstraction to the existing solutions. And again, inspired by this Kähler metric problem by the theorem of Matsushima-Lichner and independently Lichner-Riggs. Under this technical assumption, we are able to prove that if there are solutions, then the Lie algebra of homomorphisms must be reductive. So again, that's another way to prove you have no solutions. And it's a kind of standard now. The type of proof is moment maps.
So it involves flows and this kind of...
No, it's more algebraic than that.
Okay.
The only things you need are symplectic forms. You have to integrate, so it has to be compact. So this alpha and beta has to be zero. Positive. But the manipulation is algebraic. I mean, the way in which we adapt it comes from work by one from Rutgers, if you like. The way he writes it in the Kähler metric case is very abstract, and you can just adapt it here or anywhere. So it's formal. So now this was the abstract theory. I now want to return to the gravitating vortices, try to apply this theory in this case. So just remind you, we have a Riemann surface. That means there is no, I mean, this term, this kind of term disappears in this Kähler equation. Okay, this is a four form, so it vanishes. So you have this one. And, well, here is in this special case the value of t, okay, the constant. So the case which is interesting for physicists means c equals 0 implies well, by this, if this is 0, then chi must be, the Euler characteristic must be positive, so you are on the truth there. Okay. In this case, Yi and Yang, the one from whom we learned that this is actually interesting for physicists, already had proved that there is if you have some technical condition, or some condition, then there are solutions. He constructs solutions. What constructs? He finds that they exist. So if you have a divisor and its degree satisfies the usual bound you need to solve the equation, the vortex equation in Martin. I mean, the normalizations are not the same as in Martin-Stock, but it is the same. Okay, this is Bradlaugh's. I think this is Bradlaugh's bound. Okay, in his talk. Then, if you assume this condition, there are solutions. Or if you assume this other condition, I mean, there are only 2 points in the effective divisor, and they have the same multiplicities, then there are also solutions on P1. Okay? In his paper, this is in Communications Mathematics Physics, he mentioned this is a technical restriction. He doesn't know whether it's actually can be dropped. But if you know GIT, this is the first example you studied. This condition appears in Manford's book. I mean, this condition is GIT stability for the divisor as a point here. And the other one is strictly polystability, meaning it's all disclosed. Mm-hmm. So we make this conjecture. Okay, I mean, I think it's natural. And well, the attempts we make in the past to prove this conjecture seem to be too naive. No? So we are now working. We have work in progress to prove it using the weak geodesics. We hope to prove it soon, but we are still working on it. But we have partial results, and I will mention the ones I can explain without weak geodesics, which corresponds to the case in which the divisor has very few points, 1 or 2. Okay. This is next. So, if the divisor is just okay, there are no solutions. This comes directly from the abstractions I mentioned, because in this case you can compute, because you're in P1, you can write phi is a polynomial. It's has one root, so you can compute the homomorphism is not reductive. Okay, so this was a conjecture by Yang a long time ago. We can do a little bit more. And prove if your divisor has 2 points, and then this is the condition that Dan wrote. Yeah. Okay. This must happen. I mean, you can't put here different multiplicities. And again, the computation is a kind of long integration, but you can do it. And you find that unless these two are equal, because what you get is a multiple of this in the Futaki invariant, this Futaki invariant doesn't vanish, and so there are no solutions. Okay. We are still in genus 0. Now let's see. I mean, in genus 1 you can say a little bit, but maybe I can mention it later. genus 1 hasn't been studied in depth yet. But in genus greater than 2, greater than or equal to 2, we have an effective bound. Okay, assume that you are in the range in which you know there are solutions of the vortex equation. Okay, I'm fixing the volume to be 2 pi. That's okay. Then there is this bound, and if the parameter, the coupling constant alpha is not too large, is between 0 and that, then you know there are solutions and they are unique. And this is continuity method with using the moment maps again and some a priori estimates that actually make you forced to define this. We don't know yet what happens when alpha is greater than this. So I'm conjecture still it works, we don't know. Maybe I could mention. This means we can construct a moduli space of complex structures on a Riemann surface of genus greater than or equal to 2, decorated by an effective divisor. It's kind of a vortex type moduli space. It's like, you could call it that way. And I think the last slide, maybe I'm too fast. Okay. Is about, again, the general problem. Some existence results in the general case, but in the weak coupling limit. I mean, when the constant alpha, well, I make first alpha equal to beta, so this equation may be more familiar, the first one. And when alpha is 0, what you get is the first equation is was solved by Moduli and using stability for what he called simple pairs. And the second one, with alpha 0, as I said, is the famous constant scalar Kähler metric condition. So it's natural to try to move a little bit alpha, but make it close to 0. And also you can try to vary the Kähler class of the symplectic structure omega. Okay? So it works by using some implicit function theorem and Banach spaces. Sure. What you can prove is that if you have a simple pair, that was defined by Ignacy. It means the reductive. It's a bit technical. The semi-simple elements of the gauge group. How is it act? They don't fix the pair. Yeah. And suppose that there exists a constant scalar curvature Kähler metric on X with this some Kähler class, you call it omega naught. So we are solving the equations when this term doesn't appear. Then if the pair is Z stable, so there are solutions to this. In the first equation, then in a neighborhood of the space of coupling constants alpha and the space of where the Kähler class lives, okay, H11, there are solutions to the equation. So, for instance, you can apply it to the genus 1 case, if you like. That's something I didn't mention earlier. So at least in this for very small alphas, there are solutions. So, okay, since in physics alpha is 2 pi g, which is very small, maybe it's but this is not effective. We don't know how small it must be, so we don't really know. So this is it. Thank you. Well, here I've just mentioned the techniques to make the proof.
Okay, so any questions for this?
So, roughly speaking, your equations are a combination of Yang Mills and CSCK. But if you restrict to Kähler-Einstein equations, do you get something meaningful?
No, we tried that. Yeah, if you first attempt to try it without the ICMAT, you can't try it. So you could try is something like, I don't know, it makes sense to write something like this. So S equals the energy momentum temperature, which is kind of the gauge fields. But it doesn't work. I mean, let's see. The equation which has a moment map interpretation is a constant scalar curvature condition. This doesn't have this. So Kähler-Einstein implies that condition, and this equivalent when your Kähler class is proportional to how is it? To the first chain class of the manifold. But I mean, we tried that, and it's too involved. One problem. I mean, we could try from physics, take the trace. And you know this is zero when you take the trace, right hand side. So there's no coupling. If you try the physics. But that was the first try.
But still the first equation carries the coupling with the metric, right? Because you have to contract
the
connection.
Yeah, you're right. I could just try, but it decouples in the sense that you first solve the Einstein equation or Kähler-Einstein equation,
okay.
and then for that equation,
okay.
for that solution, you solve the other one. Okay, yes?
That's right.
Yes, that's one moduli over the other. But in this other theory, they interact. Oh, I mean, yeah, even the metric knows about the connections and the vortices.
What I was thinking about is trying to generalize the criterion in terms of test configurations.
Yeah.
To these
Yeah, that's another attempt to.
Maybe it makes sense, even if you still don't know whether there are meaningful equations, to try to understand whether there is a reasonable stability condition which you can define in terms of test configurations.
I mean, they are written in Marius' thesis on the archive. I mean, there are some test configurations written there. Okay, and there is a conjecture on some K stability in terms of some kind of Futaki, some metaplectic correction computed on these test configurations, on the limit of the test configurations. But we haven't proved that either. But yeah, that has like 10 years or 11 years now. Yeah, that's another approach.
Any more questions? So I have a question which is maybe a bit naive, but relates to what you said. So there is this application of the equivortice equations to topology of Higgs bundles, right?
Yeah.
When you have this gravitational kind of degree of freedom, do you think that there's going to be some kind of similar thing?
We have explored that.
Yeah.
On Riemann surfaces, the theory decouples.
Okay. Okay.
But on higher dimensions, it may be very interesting. It doesn't.
Yeah. For Riemann surfaces, the Hitchin equations do not involve the metric. And
yeah. When you compute the moment map, you find that it happens. You first solve the equation for the metric and then for the Higgs bundle. That's the moment map. So it's too trivial. Yeah, there are many, well, there are some people trying to find canonical metrics in terms of Higgs bundles, but this doesn't work. It doesn't seem to work, as far as I mean, maybe there is some idea, we don't know. But that's something we really tried for a few weeks.
Okay, so let's thank Luis.